Hey everyone, and welcome back to Chemical Bonds. This time, this is our next video in our chemistry series as we're getting deeper into uh, the nature of chemistry and what's going on inside the atoms. Today, we're finally moving up to talk about molecules and ionic compounds. So, one of the first things to know is that elements are going to form new compounds by bonding together. Okay, so the process can take place in two main ways we're going to discuss today. Those two main ways are through a sharing of electrons. That sharing of valence electrons would be creating a molecule, and that sharing is called a covalent bond. Um, while the other type is ionic bonding, and ionic bonding is where you have a positive ion and a negative ion, and they're bonded together through that electromagnetic force of their charges. And those tend to create salts, while covalent bonds can create all sorts of different stuff. Water, for instance, is a good example of a covalent bonded molecule. This process is going to follow a very important law, and that very important law is called the law of conservation of matter. Okay, you can't create or destroy matter. You can't do it. It doesn't happen that way. Matter is constant. Okay, so if I do a chemical reaction and I take two different things and I react them together to make something new, okay, that process doesn't remove matter from the universe, nor does it create new matter. All I'm doing is I'm changing the bonds between two elements. I'm making something new from what was there. But all the stuff I start with is going to be all the stuff I end with. That's really important. There's a type of chemistry problem called a balancing equation. And the whole process of a balanced equation is to make sure that the stuff on the reactant side of a reaction is the same as the stuff on a product side of a reaction. Okay, you don't create new matter, you don't destroy the matter. Okay, all reactions, everything follows the law of conservation of matter. Well, technically, it's the law of conservation of mass and energy, if you really want to get into it. That's a bit beyond us, that they kind of combine together in a way. But ultimately, matter is not created or destroyed. You can only change its form. Just think of it like that. And that's really honestly true at all levels. So ultimately, when I combine elements together and I create molecules, the new molecule is going to have properties that are different than the elements that it's made from. So if you look at oxygen, that's a gas that's important for respiration. If you look at hydrogen gas, it's a flammable reactive gas, the whole Hindenburg thing. But you can combine them together, one oxygen, two hydrogens, and create water. And water is this powerful solvent. Water is vital for life. When you're looking at a planet and you're asking yourself, hey, can that planet have life? And any star, right? If we're going out, we're trying to find extraterrestrial life. The big question we ask ourselves is, does it have water? Is that water liquid? Is that planet far enough from the sun that the water on it is going to be liquid? Because it's so important for life. Okay. Hydrogen gas, oxygen, very different than water, but they make it up. So there's this idea of emergent properties. The properties are going to be different between the molecules that we've made and the stuff it came from. That's really, really, really important. Ultimately, the properties depend on the elements that make them up, as well as how those elements are arranged. So I could take carbon and hydrogen, for example. Carbon and hydrogen combine together and create hydrocarbons. If I don't have too much, I'll create something called methane gas. Methane gas is a carbon bonded to four hydrogens. Okay. But you can also have, say, gasoline. Okay, octane has 8 carbons, right, and a ton of hydrogens. And it keeps going on. You have synthetic oils. If you toss in just like one oxygen atom, you can make all sorts of new stuff with it too. So there's a ton of different things you can make with just a few elements. Okay. Benzene is another one that's just carbon hydrogen, and that's totally different. That's a totally different compound than methane or gasoline or any of these. So how I arrange them and how I make those bonds and what elements I have are going to change things a lot. Even adding one more oxygen to H2O. If I have H2O2, I have hydrogen peroxide. It's that brown bottle you might have in the medicine cabinet, kind of bubbles up when you put it on a wound. Okay, that's not water. That's not something you should be drinking. It's totally different properties because of the number of atoms and the way those atoms are arranged with each other. So ultimately, what we have to look at now is what are called chemical formula. So a chemical formula, I've got a few examples here. I've got water, I've got hydrogen peroxide, I've got ammonia here. They tell you what elements are bonded together and what the ratio is. Okay, so here I've got H2O. The water's got 2 hydrogens and 1 oxygen. Okay, so if you look at it, what it says is H, that's the elemental symbol for hydrogen. And there's this subscript that says 2. Okay, that 2 tells me that there's 2 hydrogens. You never, ever, 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 ever mess with the subscripts, okay? Because you'll change the molecule itself. Now, oxygen doesn't have a subscript after it because it's just 1. Ultimately, chemists are lazy, and we don't want to include a bunch of numbers we don't need to, so we leave off the 1. But if you move to hydrogen peroxide, you have H2O2, so there's 2 hydrogens and 2 oxygens. Now, if I wanted to say I have 2 water molecules, I'd put a 2 in front of the H2O. I would say 2, capital H, lowercase 2, or subscript 2, O. Okay? 2 water molecules, 3 water molecules, 20 water molecules. A lot of people make the mistake and they try to start changing the subscripts. They think that's where they need to change stuff, especially if you're doing like a balancing equation. They'll start messing around in there. And when you do, you change the molecule that you're talking about, and it's bad news. Another example I have down there is ammonia NH3, very common molecule to deal with. And of course, ultimately, what we're doing is we're describing what elements make up a molecule. So I've got a water molecule down there for you to look at. Those sorts of pictures are what we're trying to drive towards. We're going to probably make those kinds of images inside of a programming language like Scratch, or if you prefer, Unity. Ultimately, all the bonding that we're going to be talking about today ultimately takes place with the valence electrons. The valence electrons are the outermost electrons of any atom. So pictured here, we got the nucleus of the atom. This atom's got 3 orbitals going on, and in that outermost orbital is its valence electron. So the inner stuff doesn't really matter. In fact, there's an entire scheme of drawing molecules or elements where you just look at the valence shell called Lewis dot diagrams. We're not going to go into those this year, I don't think. I have in the past sometimes, but ultimately the valence shells are what is really important for chemical bonding. Everything inside inside the atom that isn't the valence shells, like those inner shells, they're not going to bond. They're not going to be involved. So we mentioned ions and ionic compounds. Well, ions also look at the valence shell, and what happens is you have, like, say, sodium, okay, group 1A element. It's got one valence electron. Okay. One valence electron's really, really far from having a full valence shell. If I have a full valence shell and I'm like a noble gas, I'm not interested in bonding with anything else. In fact, things in nature are tending to bond in such a way wherein either through sharing or through the loss of electrons, they get a full valence shell. So the easiest way in the world for sodium to get a full valence shell would be if that one little electron that's not that's just sitting out there by itself in the valence just went away. And so that's what it does. It actually loses that electron to another element, and usually it's an element that has 7 in its valence. Because if I have 7 in my valence and I grab up one more, then I hit that magic number 8, and I'm like a noble gas. So for a ion, you're actually going to either add or subtract electrons. And this is important because you will be asked to create Bohr models. Obviously, these are Bohr model diagrams that you're looking at right here. And really, the procedure is the same as with all Bohr models, except at the end, you're going to either add or subtract from the electrons. Usually just 1 or 2 electrons are going to get removed or added, and the point being that you create a full valence. Okay, so the process would be identical to what you did previously with Bohr models, but you would then at that last step remove 1 or add 1. The tricky part is that because an electron is negatively charged, when we remove an electron, we show a positive symbol, positive sign. So Na positive is a sodium atom that has lost 1 electron. Okay, so that can sometimes be tricky for folks, but usually if I have a negative ion, I've gained electrons, and if I have a positive ion, I've lost electrons. Okay, because ultimately it's not looking at the number of electrons, it's looking at the charge on the electrons. The electrons are always negatively charged, so losing an electron gives me a positive charge overall, and gaining an electron gives me a negative charge overall, and positive is going to be attracted to negative. That's what's going to create our ionic bonds. Okay? So here I've got that kind of illustrated for us with sodium and chloride, also known as table salt. So a chlorine atom can grab a sodium atom's electron, and by doing that becomes a chloride ion. So chlorine is the atom, chloride is the ion, and that actually works with all of them. Fluorine is the atom, fluoride is the ion. Bromine is the atom, bromide is the ion. Okay, that only works towards the nonmetal atom. The nonmetal atom becomes an IDE ending. I'm not going to be too particular about your use of that, but just be aware that some people use that little bit of nomenclature to kind of deceive you sometimes. There's been a lot of cases I've seen where people will take the information from the element and apply it to the ion. A really popular example of this is fluorine and fluoride. Fluorine gas is actually very dangerous for you. Fluoride helps with your teeth. And a lot of people will tell you facts about fluorine and try to say that that's applied to fluoride. And actually, by losing that one or gaining that 1 electron, it becomes much more stable, takes on like the octet of a noble gas, and it's not as interested in reactively grabbing an electron the way that its atomic counterpart would be. Nature doesn't like charge imbalance. That is a very, very important thing within nature. It doesn't like charges to be in balance. It's going to balance these out. As a result, sodium atoms and Sodium ions and chloride ions are going to always go next to each other. So you have positives and negatives kind of stacking in this repeating pattern. The reason is it gives you a net zero charge for the unit. So you can look at that crystal of table salt and go, well, there's no charge. Everything inside it, all those ions are charged. But because they partner up and create these ionic bonds, you have a net unit that is not charged. And it actually extends into space. It creates a three-dimensional crystal. Okay, so all the crystals that you've probably seen actually are in fact repeating patterns of ions, positives and negatives, stacking up around each other in such a way that the overall picture is neutral. Okay, so here you've got a representation where the green spheres are chloride ions and the blue spheres are sodium ions. Okay, and the green is going to stack next to the blues are going to stack next to the greens, and you create this what's called a crystal lattice structure. That term is way important, and that crystal lattice structure is actually what we're going to break apart to make hot and cold packs later on. But realistically, the cool thing about this is it creates such beautifully diverse and interesting materials. So most crystals are taking on this sort of repeating pattern, and that's what gives the crystal its structure. So if you look at some crystals, they'll be like hexagonal, or maybe it's like a square as it's growing out, because ultimately it's stacking one after another after another after another, so that the positives and the negatives are always stacking next to each other and balancing out. There's no charge imbalances. It's really, really cool. So the other type of bonding that I mentioned is covalent bonding. And in covalent bonding, you're still ultimately trying to get to this full octet. This is the big goal, is to have your valence shell filled. So water molecules do this not through stealing an electron, like we saw with sodium chloride, but through sharing electrons. Okay, so ultimately in a covalent bond, what happens is the valence shell of one atom bonds to the valence shell of another atom, and they both share the electron in there. And by sharing those electrons and their valence shells, they end up creating a structure where everyone has their full octet, where everyone has a full valence shell, and you're all moving towards trying to look like those noble gases that don't react. Okay. The thing about this is that those bonds aren't always equal. Okay. So just because I'm sharing with someone, right, doesn't mean that it's an equal sharing. Maybe you share a Nintendo Switch with your brother or sister, but one of you tends to have it more often than the other. That's what the atoms actually do inside of a lot of these molecules. Depending upon how uneven the sharing is, determines whether something is polar or not. So a polar covalent bond, like you would find in water, results because the oxygen is much more attractive to electrons than the hydrogen is. And as a result, the electrons end up spending much more time hanging out with oxygen than they do with hydrogen. And that results in partial charges to the oxygen and the hydrogen. If you look at this picture, there's this weird squiggle. That weird squiggle is a lowercase delta. Okay, so delta positives on the hydrogens and delta negatives on the oxygens are partial negative and positive charges. And what that does is actually creates intermolecular forces. In this case, called hydrogen bonds. The intermolecular forces are attractions of positives and negatives to one another across molecules. Okay, so there is no actual sharing going on, but it helps determine how they arrange themselves in space and how they're going to float next to each other. And this is actually the reason that water is such a cool solvent. Water can tear things apart so readily because it's got these partial positives and partial negatives, and those are really great at lining up to, say, the full positives and negatives on a sodium chloride. So you put a piece of salt into water, and the water tears it apart. Okay, the salt disappears and becomes invisible very quickly. It dissolves, right? And that's because the oxygens are partially negatively charged because they've stolen the electrons effectively. They're sharing it with air quotes around that, right? And as a result, they can grab positively charged sodium atoms really well. And the hydrogens can grab negatively charged chloride ions really well. And that is ultimately why water is a really great solvent. Water's got a lot of very cool properties, and the hydrogen bonds that result between molecules is a huge part of that reasoning. Um, so when do you know which one's going to occur? Obviously, we have these ions and we have these molecules, and how do you know if it's going to make an ionic compound or if it's going to make a molecular compound? The answer is that you got to look at the type of atom it is, whether it's a metal or a non-metal. So if you see in this picture here, we have red atoms marked as metals. We have blue non-metal atoms, and then we have something called metalloids or semi-metals is another word for that. Um, the non-metal atoms will bond together to create molecules. Okay, and that's got a huge, massive diversity. If you look at what carbon and hydrogen alone can do, you can make ridiculous amounts of molecules. Especially if you start digging into organic chemistry, toss in some oxygen, toss in some nitrogen, you can just go crazy with all the different varieties. Okay. Um, However, if a metal atom bonds to a non-metal atom, you're going to create an ion. So chlorine and sodium, chlorine's going to steal the electron from sodium, and you're going to have a positively charged sodium atom or ion attracted to a chloride ion. Okay. Um, that's really about it. Ultimately, there's Quizlet decks you're going to want to check out for all of this. We are going to be using these sorts of models to create our own models inside Scratch or another programming language. Some of you guys want to look at Unity. That's totally cool. Um, Ultimately, that is the goal at this point, is to try to take these different models that Bohr has shown us and try to express that through code, um, which you're going to be working on in class for the next couple of weeks. Hopefully, you got a little bit about this. Um, Very, very important stuff, the last couple of videos. Very fundamental to our chemistry understanding. So hopefully you had a good time, and I will see you in class tomorrow.